Hello everyone, welcome back to the e-learning modules for Underhood thermal application using SimLab as the preprocessor and AcuSolve as the solver. This is the third video of the series. We will connect two surface mesh bodies together, place the volume mesh controls, and CFD mesh the model. Picking up from the previous video where we have generated the mesh for the canopy and all of the relevant parts such as the MRF region and two heat exchangers. And we have also successfully generated a wrapped surface mesh for the engine. In this video, I will show you how we can create a surrounding fluid domain and ultimately generate a CFD mesh that is ready for flow setup. Turning on the section cut in the Y normal direction, we see that there is overlapping or intersection between the engine and the rails of the canopy. What we want to do is to boolean the engine and the canopy together. The input gonna be mesh, and we need to choose combine operation. And we don't want to retain internal faces, and we need to enable local remesh. When the boolean operation has been done, we can turn on the section cut again. So the engine and the rail is now connected. We merged the engine and the canopy together. This is one of the most important Boolean operations ever. In this case, I will meticulously check for intersection and free edges if available. Okay, so there is no elemental intersection. Now we need to check for free edges. Two free edges here. If you see free edges, we can manually stitch these together. Into mesh, modify and create. We will create a tri-element. One fixed. We can do this one too. All free edges are now resolved. Okay, now we check for intersection and free edges again, just to make sure. Okay. The next step is to create a big surrounding fluid domain. We can do this by going to geometry and create a cuboid. Let's choose this as the bounding body. And we would like to change into meters so that we can easily put large measurements. The length is going to be 25 meters. The height and the width going to be 12 meters each. Okay, I will position it to be on the top. the body type generated, I will use mesh with the mesh size of 0.4 meters. Now click OK. And we name this as domain. If you turn on the cross section in the X normal direction, you see there is a lot of overlapping, solid overlapping with our surface mesh body. Now we merge the domain and the canopy together. Let's change the color to blue. Now let's isolate the two heat exchangers and the MRF region. I want to create two shared faces for each heat exchangers, and then I'll merge it with the domain. I'll go into surface selection and select two faces for each heat exchangers, and it's gonna be two axial faces. Create from faces, duplicate and make shared faces. Make sure this is chosen. I'll merge the faces that I created and shared to the domain. If you do it correctly, when you're turning on the cross section, you see 4 yellow topologically connected faces on each heat exchangers. Let's change the color to light green. 4 shared edges or yellow faces for each heat exchangers. Okay, so we're gonna do the same for the MRF region. Duplicate and make shared faces. I'll take the MRF and I'll merge it with the domain, just like how I did it with the 2 heat exchangers. Looking for yellow edges surrounding the MRF region. Now we can place body mesh control on the 2 heat exchangers and the MRF region so that we have finer elements in the zone where flow have the most actions. Mesh control, I will choose body based for the 2 heat exchangers. I will name this mesh control as heat exchanger 7mm body mesh control, and I will pick two bodies, the large one and the small one. Make sure the element is going to be tab 4. This is 7mm. It's going to be 15mm maximum angle per element. Click OK. And another body mesh control for the MRF region. Okay. We also need one battery layers for each domain. One is for the MRF region and one is for the main fluid domain. I'll call it MRF interface. We choose fraction of the mesh size as a definition, and it's going to be 0.5 for the first layer thickness. I only need one layers, and the termination policy I will choose squeeze. Click OK to apply changes. I will create a face group with no battery layers. I'll name this no battery layers 1. And 2 axial faces for each heat exchanger is going to be no battery layers 2. And last but not least is to place a refinement mesh control so that we can step down from a really coarse mesh size outside to a really fine mesh size inside the region of interest. Mesh control, and we would like to do regional mesh control. It's going to be a cuboid. We'll define it using a body. Let's change the dimension to meter so that it's easier to resize the refinement zone. I want to position the refinement zone so that it's right in the middle of all 4 dimensions to the region of interest. For the lateral side, we move it down 2 meters. It's going to be -2 in the box. And the element size of this region going to be 0.15 meters. We also need to make sure that the bottom is also right in the middle too. Make sure all parts is selected. Click OK. And we want to place 2 more so that we have a smooth transition from the outside to the inside. We'll move the lateral side to 3 meters back. Maybe half a meter more. The second refinement zone gonna be 0.075 meters. And make sure all bodies is selected. And the last one. Okay, he's right in the middle. Okay, the last regional mesh control gonna be 0.02 meters. Click OK to apply changes. At this stage, we're almost ready to CFD mesh. Because in the wrapping workflow, we would like to use a face-based CFD mesh. In face-based CFD mesh, there's going to be 3 inputs. The first one going to be all of the faces available on screen. The second one is the ignore boundary creation on the faces. So these are where we're going to put our face group. And lastly is identify fluid volume by node. In the face-based CFD meshing, we need to feed the mesher so that it understands which region is the fluid and which region is the solid. So we're going to back out one step and create the nodes for the meshers. The golden rule of thumb is to understand that when we have 4 fluid domain, it means that we need 4 nodes. We go into mesh ribbon and then nodes, click create, and we want to create the midpoint node. I'm going to choose 2 nodes. Click create. It will create the node right in the middle of the fluid. And we're going to do the same for the other 3 nodes. If we hide this, you see that the node is created right in the middle of the fluid domain. For the MRF region, we need to be a little bit more careful. We need to hide the interface, and we need to place the node so that the midpoint isn't accidentally placed inside the solid of the blade. Okay, so we have 4 bodies and we have 4 nodes. Now we are ready to CFD mesh. Click on CFD. For the faces, I will choose all of the available faces on screen by window selecting. Identify fluid volume by node. We're going to select the 4 nodes that we have created a moment ago. 4. And ignore battery creation on faces. First of all, I wish to ignore the battery on the 6 faces outside of the big fluid domain. And I also want to ignore on the axial faces of the heat exchangers. I also don't want to create battery on the engine intake, the exhaust tip number 1 and exhaust tip number 2. The first layer thickness, I will choose fraction of the mesh size with the first layer thickness factor of 0.15. I want 6 layers in total at the constant growth rate of 1.3. And the average element size is going to be 0.4 meters. When everything is input, click OK to start the measure. When the mesh has been completed, we can turn on the cross-section to take a look at the TED elements. Let's turn it into Z normal direction. At a glance, we can see that the regional mesh control is respected really well, where we have a coarse mesh size outside and then further refined inside. When finished meshing, you can see that the solid inside and the fluid domain is merged into one part. We need to unmerge them. So this is the solid, and where we have the battery layers is the fluid domain. Click on the domain and right click and unmerge. After unmerging, there will be a lot of parts, and most of them just the solid domain inside. What we need to do is to find the fluid region. It's gonna be, I know it's gonna be the MRF region. This one, the heat exchangers region, and most importantly is the big fluid domain. Okay, and the smaller heat exchangers here. So we have 4 fluid domain, and the other ones are just solid. Now we can select all of them and simply click delete. Let's turn on the cross section. So we have refinement zone, really coarse from the outside and getting finer and finer to the region of interest. And we see that there is no battery collapsing near the interface between the heat exchangers and the fluid domain. There is one layer that we put as a mesh control on the interface between the MRF and the main fluid domain. This is the engine intake. There is no battery layers because we ignored when we set the CFD mesh. And the small heat exchanger looks good too. If you go back into the MRF, we also need to unmerge the fan blade out of the region. Right click and unmerge. Okay, so we need to delete the purple solid. Display all parts again. Now let's take a look at the cross section between the exhaust tip. We can turn off the mesh for a little bit and then position the section cut so that it's cut right through this exhaust tip, and it's going to be in Z normal direction. Now hide the cat and enable the mesh. Okay, nice curve on the battery layers, and there is no battery layers on the exhaust tip as we set in the CFD mesh. And we can take a look for the other exhaust tip too. Okay, so no battery layers, and on the exhaust tip, and battery layers curve really nice. Okay, now we can rename this. So the yellow is gonna be large heat exchangers. Large heat exchangers. The blue gonna be the MRF region. And then there is a domain. And lastly is a smaller heat exchangers in the back. Okay. And that concluded our meshing videos. In the next video, I will show you how to do the flow setup. This workflow requires an advanced battery condition that hasn't been covered in any e-learning modules yet.